Welcome back to our lecture Machine Learning, and in this week we want to continue our discussion of neural networks of deep learning. And while in the last videos we have talked about the fundamentals of neural networks, like how a neural network is composed of, right, like these different layers and the activation functions, along with the training of these neural networks using backpropagation. In these videos we want to talk about, let's say, some advanced principles and some tips and tricks which you take into account when operating with neural networks, when training neural networks. So we want to start about, like we call it here, structured data, because what we have seen so far is like the basic neural network. We talked about this multi-layer perceptron, these fully connected feed-forward neural networks. And these neural networks are somehow, let's say, the most general and the most agnostic to the underlying task models you can use. So what I mean with this is that in many applications you have specific data at hand, you have specific tasks at hand. So for example, if you have images, you rarely are using like a standard fully connected neural network, but you use so-called convolutional layers, which we talk about in a second in more detail. And there are other kind of specific layers, architectures, which are designed for specific data types. So for example, for temporal data, for sequential data, you can use so-called recurrent layers. Or if you have graph data at hand and you want to classify graphs or working with graphs, you want to use so-called graph convolutional layers. So here, this is what we quickly want to talk about in the following. Convolutional layers for images, quite prominent. These other ones here, we will cover in our advanced lectures in an upcoming semester. So why do we want to work on specific data types, or why do we want to have specific layers for specific data types? So the point is that if we can exploit some known structure of the data, we can often better generalize and often easier train our models. A very famous term recently is this so-called inductive bias. So if we know how the data or how the task if we have some prior knowledge about the data or the task at hand, we want to encode this into our machine learning model, simply speaking, right? So if we know that these are images, then we specifically want to design layers which are aware of that these are images, which preserve specific properties, for example, which are inherent to images, right? While the fully connected neural network is really like a complete black box where every input can interact, so to say, with every other input from the next output, so to say. We want to potentially induce more inductive bias to our architectures to handle this underlying data in a much better way. So this inductive bias, or in general the prior knowledge about the structure of our data, helps us then to learn better, to generalize better, right? You know that generalization is actually the final goal of what we are doing here with these machine learning models. And again, you can think about these different pieces still as Lego pieces, right? You can have like fully connected layers, you can have these convolutional layers, you can have recurrent layers, and so on and so forth. At the end of the day, you can plug these different pieces together, as we discussed in the last videos already. So as said, we want to talk here in this video just about one type of layer, convolutional layer, specifically designed for images, and to give you the motivation why we want to do this. So let's say we want to work with images. We want to classify images, whether we have specific people on an image, for example, okay? So images are usually rather large, right? Let's say we have a 100 times 100 pixel image, right? Which is even rather smallish still. And we want to use it in a neural network. So what it means is, if we want to use a fully connected neural network, the one you have learned so far, is that we need many, many weights to learn from this image. Remember, every neuron here in this hidden layer, right? Let's say this is the first hidden layer of our neural network. Every neuron here receives the input the weighted, right, a weighted version of the corresponding pixel, right? So every pixel is weighted and goes to this specific neuron, right? So you can imagine what this means, right? If we have here already 100 times 100 pixels, and even for this single neuron we need all of this, this quickly blows up, right? So here's an example, right? Let's say we have this image and we have this one hidden layer with 1000 units, right? So here we have 1000 units. Then we already need 10 million parameters, 10 million weights of this very simplistic neural network, right? Because just the input data is already so huge, okay? So we have, simply speaking, too many degrees of freedom, right? Because every edge here can essentially have its own weight, right? And then the number of weights quickly explodes. And you can imagine what this means, right? We have far too much flexibility, right? We have so many parameters. It's not only slow to train, but it might also very easily overfit to your specific training data at hand. So what we then do is we use these specific layers, these convolutional layers we will talk about in a second, to, for example, reduce on one hand the reduce the amount of parameters, but we specifically want to exploit the, let's say, local correlation of pixel values, right? Because in an image, we know, for example, that neighboring pixels, they might have a similar color value, right? Or they correspond to specific edges in the image, right? And we somehow want to exploit this kind of property in our neural network architecture. And what we see in a second is that we use these so-called convolutional layers, and for convolutional layers we can quickly reduce the number of parameters to a reasonable size, so to say. So what are these convolutional layers? So let's start, let's say from a theoretical point of view, what is a convolution technically? So for continuous data, for continuous functions, a convolution is defined here as given the following, right? You have like an input signal x, okay, whatever this is, right? Here it's a one-dimensional signal. Let's say it's some continuous function with a one argument. And then you have a so-called kernel or so-called filter k, which is also like a continuous function. And then the convolution is defined as you see it here, right? If we have the convolution of x and k at a specific time t, it's the integral over the full domain minus infinity to infinity, where we evaluate our function. Here we're looking at t, here at the position t minus tau, and here at tau. Essentially, we have here like a shift at t minus the tau, and here it's added at the tau. So we have like a sliding window, so to say. We weight this signal with a specific at a specific position, right? If you think about like a continuous signal here, this is x, and this is, let's say, the kernel, the filter, right? We are, so to say, sliding this kernel over the signal. So technically speaking, here we are sliding the signal over the kernel. It's in the other way around, but you can imagine that this signal is slided, then we are weighting it accordingly by this product. So this is the convolution in a continuous sense. And usually, of course, we are not in a continuous world. We're operating in a discrete world, like it's a like one row, let's say, of an image, right? It's like a discrete event, a discrete world. We have 100 elements, for example. Then it's accordingly defined by summing up over the full domain, and we're evaluating our function at a specific position, shifted, and here at the corresponding shift, so to say. Okay, so that's a discrete variant. So it becomes more clear later in some kind of animation. So if we look at a 2D setting where we do a 2D convolution, then it looks like this here again. Of course, our input is also now two-dimensional, like an image is a two-dimensional array of pixel values, right? We have position L and position M, and here we have our kernel again, which is also at two positions. And again, note what we're doing, right? If we have here the convolution between the image and the kernel, and we want to know what is the output at I and j, we have to evaluate it here essentially at I and j shifted, and then we look at here at the position of this image, for example. So this is indeed a convolution. This, however, is usually not what is done in modern deep learning frameworks. Usually what is done, even though it's called convolution, we are looking at so-called cross-correlation. In the cross-correlation, we're usually switching the roles, so to say, or the indices of the image and the kernel. What I mean with this is the following. So here you see it, right? If we do a cross convolution, it more or less looks the same. We have here our input signal, and here we have the convolution, the kernel, sorry. And then we are doing this kind of operation. What does this mean? So let's say we have here our image, right? A large image, 100 times 100 pixels, right? And we have our kernel, which is usually of smaller size. So this is our image. Let me do it differently. So this is our kernel K. This is our image X. And this has size, let's say, L and M. Okay. So what we are doing is essentially we're taking this kernel and we slide it over the image. Okay, the kernel is like a smaller patch, if you want to say so, right, of size L and M, and then we evaluate it at this position. Okay, so to get the value at coordinate I and j after the convolution, right, we take our image and we put on top the kernel, right? We evaluate it here, for example, right? And we multiply the corresponding values and sum it up. And then what we are getting out is the value we are getting for this x hat. Okay, so the x hat, for example, here is again our big image, and this value here is a result of evaluating this patch. Okay, we're multiplying this patch of image, multiply with the kernel, and then this gives you the output here. Or similarly, let's say you have here a specific value, right? So the value here is obtained by sliding this kernel over this piece, or putting this kernel over this piece, okay? So for this, let's actually look at this example. So here you see it, right? So let's say we have a specific kernel, right? And the kernel, or the sliding window, has here the coordinate, the values 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? So this is our kernel. So to say the window we are sliding over the image, right? And you see it here, for example, if we put this on top here, this kernel at this position, and let's say this is an image which has a pixel values 1, 1, 1, 0, 0, and so on and so forth, right? Then what we are seeing is we are multiplying here these corresponding values, right? 1 with 1, 1 with 0, 1 with 1, and so on and so forth, right? We sum it up, and this leads to the value of 4. Okay, so this kernel is put above this patch, and then we get as an output the convolved feature, so to say. And now from this part, we continue, right? So we no longer just apply this kernel here, but we move it also to the next position, okay? And starting from this, you see now that the animation is running, right? You get the sliding window, right? It's evaluated at this position, at the next position, and then it goes to the next row, and so on and so forth, right? We evaluate this kernel at every position until at the output you see we have this, here in this case, a 3x3 output, which are these convolved features. So the important part here is indeed that we see that we exploit, so to say, the locality of these pixel values, right? Because we are somehow aggregating these local patches in the image. So let me go back here one more time. And this is indeed what you see here formally written in this lower part, simply speaking, right? So you have here the output coordinates, so to say, after the convolution. And how do you get it? You get it by putting this kernel and multiplying it with the corresponding position, right, where you evaluate the full kernel, right? So L and M is the size of this kernel, and you have always here this corresponding shift to get the correct pixel value. Okay, so what is seen here is indeed really just what we have shown here in this for the upper left, and also then for the remaining ones. Okay, so what is important to know is that these kernel matrices, and that's the full point of a neural network, these matrices here, these filters, they are also unknown, so to say. They are parametric. So we don't a priori say that we have here 1, 0, 1, 0, 1, 0, and so on and so forth. But these filters, they are also learned. Okay, so you can imagine that these now here are like parameters W1, W2, W3, and so on and so forth, right? So we have here nine parameters. And these parameters are learned when we do the learning of our neural network. But now you see already the big advantage, right? So instead of having a fully connected neural network, where in this case, for example, we would have here 5 times 5 weights for every neuron, right? So we have 5 times 5, everyone interacts with everyone. Here we only have 9 weights we have to train. Okay, we have 9 weights, and this is applied to every of these different pieces here by sliding the same weight, so to say, over the window. And this is why we reduce the number of parameters. So technically this is called a weight sharing, right? Because these weights we are using to get this output features are shared, so to say, to also get this output features. They are just applied to different input patch, so to say. So as a nice homework for yourself is every convolutional layers where you do the sliding over this image, getting this kind of an output here, for example, this can of course also be represented by a fully connected neural network. Okay, and this is a nice homework for you. So think about like here this image, 5 times 5 image, right? So 25 features in, and we have here in this case 3 times 3 features out, right? 9 features out, 25 in, 9 out. Think about the fully connected neural network, which exactly represent this convolution with these weights 1 to W1, W9. Okay, so every convolution layer can be represented by a fully connected neural network, and then you nicely see that many of these parameters here are shared. So this W1 will appear multiple times, right? And we don't use a full fully connected matrix, but we have a specific structure of our weight matrices. So please do this as a nice homework. Okay, so this is one point I want to raise here. So the number of parameters is getting much smaller because we are not using a fully connected neural network. And another point is, why this is helpful, is that usually we are not only applying one of these filters to our image, right? So these filters, as I said, they are learned, right? So we have these, I don't know, 3 times 3 filters, which are learned. And as you see it here in this video, depending how your filter looks like, you're extracting different features from your image, okay? So specifically, you can also think about like, let's say you have, for example, such kind of a filter, 1, 1, 1, minus 1, minus 1, minus 1, and 0, 0, 0, let's say, right? So this kind of filter, will extract, for example, specific kind of edges, right? Because we are looking here at high values, and then we are just subtracting these values. And if you have an image, for example, where it's all black, right? So let's say you have an image which is all black. So you have here only black pixels, and here also only black pixels, right? Then, of course, if you look at these values and you subtract the other ones, so let's say this is black and the next one's also black, then it's 0. However, if you have an image which has like red pixel and then black pixel, right? Now you see if you have red minus black, right? Red minus black, so to say, we get a value, okay? So such a filter, for example, can highlight, so to say, edges along this axis, right? Color changes along this edges, which correspond to edges. And you see this here in the animation. Different filters, as you see, highlight different structure of the image. And this is why these convolution filters are very helpful to use, for example, for image data. Okay. So in general, and going back again to this slide, this is what you then see here as well. So in general, these convolutions are not only applied once, but they are applied on often so-called different channels, right? Different channels could mean, for example, what I just said, that we have, for example, multiple versions, so to say, of this image in, right? Because we have, let's say we have started with an image and we apply 2 different filters on it, then we get 2 different kind of feature extractions out. And this is often called like multiple channels, okay? So then the number of parameters we technically have is not only the number of parameters of our filter, right, L times N, but we might have multiple channels in and multiple channels out, which of course multiply then the number of parameters, okay? So really think about like, as we have seen here in this video, that we have multiple versions of the extracted features which correspond to these channels. And if we have multiple channels in, and we apply all these different filters on top of it, we also get multiple channels out. Okay. Good. So this is more or less the basic principle of a convolutional layer, right? Again, you have like a filter which is like a sliding window over the image, which then extracts you these features. And then we save parameters, but we exploit that images have this kind of locality, that pixels are similar, or that we have specific edges, for example. So it's a reasonable feature extractor for images, so to say, right? Because in a fully connected neural network, again, this upper left pixel also interacts, so to say, with the lower right, for example, right? They together can go to one neuron, right? To make some to make the output of the next layer, but this might not be really helpful because this is not how images behave. Okay, so then a few more details on this convolution. So we have already seen this actually here, right, in this example. So images are of course finite, right? And technically this convolution or the cross-correlation is over an infinite domain. Here, however, it's not finite. And then you see one issue, right? The size of the output is getting smaller if you want to apply this filter in a proper way to our image, right? And indeed, this might be undesired in some cases, right? Because now the output here, said right, has a smaller size, and you might not be able to have, you don't want this potentially, right? And you are not using every pixel to the same amount. So for example, this pixel only appears in one, so has only a role in this upper left feature, so to say, right? But this feature here, however, for example, appears twice, right? So this pixel here plays a role for this feature, but it also plays a role for this feature, right? Because also for this sliding window, it plays a role. And this might be undesired, okay? And this is where the principle of padding comes into play. Padding more or less means we pad around this image, right? We make it larger, so to say. We make this image larger, adding usually, for example, zeros around. And then we can also apply the filter, for example, here. Okay, so think about that all these, this background here is now also zeros. Then you can apply your filter here, for example, and you get another value, then in this case, it was here, right? Or of course, you can do the extreme version. You apply the filter here, right? Because of all this padded, and then you get another value here, for example. Okay, so padding essentially means we are making our image artificially larger, adding, for example, zeros around the image to make sure that if we apply our filter to it, the output, for example, is the same. Okay, so this is this principle here, the same padding where we technically add k half values on each side. So k is the size of our filter. Okay, so the other one is the valid one, which we have already seen before. Valid means we only apply the filter to the real image, meaning we don't do any padding, then we reduce the size, right? So we make the size of the image, so of the extracted feature, smaller. And then last but not least, we have the full padding, which means we add really k minus 1 to the around the image, right? If you have here the image, you can think about adding only half around it. And if you now apply the filter, we get the same size as a red one. Or you do full padding, meaning we make it even larger so that you can pad even here, like only this part, that only this real pixel is taken into account, the rest is really padded. But then the output will indeed be even larger than the red shape, okay? So usually, what means usually, so there are different solutions, but often the same or the valid padding is done, because valid means we really only use the valid pixels. We don't artificially pad, or same to preserve the original size of the red one, right? Because same means red in, red, same shape out, okay? So this is known as padding. So then there's another concept which is called strides, because often actually you potentially don't want to do the convolution really at every position, right? Again, technically, how this works is that you have here your first kernel applied, then you have here at the next position you apply it, then you apply it at the next pixel, and so on and so forth, right? And you see that this is of course highly overlapping, right? If you think about it, you have a 10 times 10 filter kernel, right? Then essentially you have all these multiple overlaps here, meaning you potentially introduce a lot of redundancy, which might make your processing slower, of course, right? And which might not help you to extract the right features, right? Because the full idea, again, of a neural network is, intuitively speaking, that we're extracting features along the way, meaningful representations. And all this redundancy might not be super helpful, right? Because you even know that redundancy might hurt also like your neural network at the end of the day. So then as an alternative, there are these so-called strides. And strides simply means that your filter is not shifted just by one pixel, but it's shifted by a larger amount, okay? So a stride just means, a stride larger than 0 means just that you shift to a larger amount, right? So it means, for example, you have here, let's say then the first, and then you have here the next one, right? So you shift it, for example, by 5 pixels here, and then again by 5 pixels, 5 pixels, 5 pixels, okay? So technically then, a stride which is larger than 1, right, because stride equal to 1 means you have like the most fine-grained view. A stride larger than 1 means you also do a downsampling of your signal, right? Think about, again, you have an, I don't know, 100 times 100 image, and you have like a kernel of size 10, and you also say a stride of 10, right? Then you have essentially disjoint sliding windows, right? So here, if this is your kernel and you have a corresponding stride of the same size, then you would apply this kernel in a disjoint way, right? So this is how it will then slide, right? It won't overlap. It will be disjoint windows. And of course, again, this will lead to a downsampling of the signal. So while you here have 100 times 100 pixels or whatever size, right, you have only then here as an output 1, 2, 3, 4, 5 times 5, for example, okay? So strides help you also to do downsampling. And indeed, strides are one way of doing this downsampling. Another way of doing this downsampling is called the pooling. And pooling is essentially a mix of doing some kind of aggregation and downsampling at the same time, if you want to think about this. So what is this specifically? So let's say, again, you have some image. Let's say here this 4 times 4 image. You can do a so-called, for example, max pooling. And a max pooling, for example, could mean that you take your patch here. Okay, you take your patch and you take the maximum across these values. Okay, so you take the maximum across these values. So technically here, if we want to make it very specific, this is here what we have shown, a max pooling with a filter of size 2 times 2, right? So this is your filter and a stride of 2, right? Because here, one filter and then you stride by 2, you have here the next filter applied. Then you have applied it here and then you have applied it here, okay? And you don't do any padding, and then you get back, so to say, a downsampled version of your image where you have done here this max pooling. So you see here it's a 6, here it's an 8, here it's a 3, and here it's a 4. Okay, so this is known as pooling, and there are different versions of pooling. So you can do max pooling, mean pooling, and norm pooling. So to look at the norm of these values, and so on and so forth. Okay, but it's another way of doing like your downsampling. So why I'm saying this here is because these are, again, building blocks which you will encounter in all these modern deep learning frameworks. You can activate, so to say, pooling to do this downsampling. You can activate these kind of convolutional filters. You can specify the sizes of the filters. You can specify the strides. You can specify whether you want to do padding or not, and so on and so forth. So the full idea then at the end is that you, with this, can build a full architecture. Okay. So for example, you start with an actual image. Here, as an example, it's size 32 times 32. Then, for example, you do a convolution, right? You do a convolution, for example, with a filter size of 5 times 5, and let's say you don't do any padding. Then you extract here features, so to say, right? And you see here that you have done 1, 2, 3, 4 different channels, so to say, right? You have learned four different convolutions, so to say, right? Again, remember, these are learned convolutions, right? Then you get 4 times these kind of extracted features, slightly smaller size, right? Because we didn't do any padding here. And then we could, for example, do a subsampling, like a specific pooling, for example, to make it smaller, right? What we have seen on the previous slide, let's say a max pooling with a kernel of size times size, 2 times 2. So we get here like smaller size, and then again we can do a 5 times 5 convolution, for example, on these 4 different channels, right? And let's say we do it in the full-blown way, so to say, right? You see here that we have here 4 images, and all of these images we apply a convolution, right? And we get here all these different kind of variants, so to say, okay? Which are here again these now extracted features. We again do a pooling, and at the end of the day, for example, right, we have here then, let's say, some hidden representation. We have learned this one after we have done another convolution. Then usually we treat this, for example, which is of rather smallish size, as a standard vector which we can now feed into a multi-layer perceptron, so to a fully connected layer, so to say, right? You see it here. We have extracted some features. We have flattened, so to say, our images, right, where we have here still images, very tiny images. We have flattened it here. We have a fully connected layer. We reduce it to, I don't know how many these are, to 10, for example. And then we can do our final softmax, for example, to do a prediction. Okay. So this is often how it works. And of course, in practice, in these modern architectures, there are much more different building blocks. But in principle, you see how it works, right? We have some raw data. We apply some convolution, some downsampling until we reach some dimensionality, which we like, right? Let's say, I don't know, 1,000 features, so to say. Then we do one last projection to the number of classes usually. Let's say we have 10 different classes. Right, so here's one layer which projected to 10 classes, and then we do a softmax to, for example, get our prediction. Okay, and this is indeed what I also said at the last video in this kind of where we generalize logistic regression. In some sense, you can think about that this first part is doing some kind of feature extraction. We learn a nice representation of images, which is informative. And then at the end, we're doing a standard classification, so to say, a logistic regression on the learned features, for example. So these are convolutional neural networks. And as you have seen, these are specifically suited for images because it has this natural view of having like a sliding window which extract reasonable features like edges or taking averages of pixel values and so on and so forth. And as said, for other kinds of data, there are also other kind of like components, so to say, we can use. So as we said already, for text and time series, we can use RNNs or transformers, which are based on the ideas of attention. We can have graph data like social networks or molecule graphs. We want to use graph neural networks. So since here, this is just an intro lecture to machine learning, we unfortunately can't discuss this in detail, but if you're interested in this, then I recommend you to watch our other lecture, which is about machine learning for graphs and sequential data, where we talk about this in much more detail. Okay, so to wrap up then this part, as you have seen, specific data types can require different kind of architectures to reduce the number of parameters or to make use of the specific structure of the data to have a specific inductive bias, exploiting how your data looks like or what are the inherent properties of your data. For example, also in images, by the way, the translation is one important aspect. For example, let's say in image classification, whether an object is here or you translate it and put it at a different position, this shouldn't change the prediction of, let's say, whether this is a car, right? If the car is here or here, this translation shouldn't change it. And the convolution essentially also takes into account, right? If you have this kind of sliding window, right, you have always the same parameters and you would extract these features here or here, you would always get, so to say, the same features in some sense. There are some more tricks and you have to be a bit more careful, but this is how you can think about this intuitively. Okay, so then let's go actually to another topic which is important besides these special architectures. And by the way, you can imagine that there are many, many different architectures and components available. But here we want to now switch again, focus a bit on talking about the training one more time. So we have seen that we can train neural networks using gradient descent, right? Meaning stochastic gradient descent or ADAM or whatever advanced version you want to use, which means we have to compute the gradient using backpropagation, then we do our update steps, okay? So there are a couple of points here we should discuss. On one hand, of course, and this is what we have already seen, is that, of course, this is a non-convex optimization problem, right? We have these complicated functions. We want to minimize the loss. Of course, it's not convex. It's some very complicated form. So then the question naturally, of course, arises, where do we start, right? And one idea is, of course, to do multiple restarts to avoid that we're getting stuck in local minima. But still, there are some points you should take into account. And indeed, the weight initialization is one important aspect of a successful training. So weight initialization means how do we initialize our weights of this neural network such that when we start from these weights, we can achieve nice training, right? And indeed, there are two important points here which we should take into account. One is the weight symmetry and the other one is the weight scale. And let's quickly talk about the weight symmetry. I guess that's very clear to see. So let's assume we have two hidden units, so two neurons in our neural network, which have exactly the same bias and exactly the same incoming outgoing weights. Okay? So meaning if we initialize it, let's say we initialize all weights with 0, which could be one idea, right? We initialize everything with 0. This indeed, however, is not a good idea, right? Because if two hidden units have exactly the same bias, so one of the parameters and the same weight terms and so on and so forth, then of course the gradient we are getting is also the same for these, right? We can't distinguish these two neurons, so to say. Why is this bad? Because now these two neurons can never learn different features, right? They are just redundant, right? They have exactly the same, they exactly learn the same information, okay? And there is no chance to escape from this, right? Because they can't be distinguished anymore, right? They have the same information, the gradient is always the same, and then of course the update will also still lead to the same result, okay? So, don't initialize, simply speaking, for example, with all zeros or with all the same weights. This is not a good idea, right? Because then you have the symmetries and you can't escape it. So one solution, of course, to break the symmetry is just to initialize these weights randomly, right? So don't do it with all zeros or any other constant value, but you have to initialize the weights in your neural network randomly, okay? However, there's one other aspect. If you do this randomly, you also have to be very careful, right? Because think about, you have one neuron which has a, let's say, a huge fan in, right? You have one neuron where many incoming signals, right? Think about like you have an image of very large size, right? And you'd say you are not aware of convolutional neural networks, right? You use a fully connected neural network, let's say, and then you have all the pixels of the image. They are incoming to this single neuron. Okay. So why is this now dangerous? It's dangerous because if the weights here are somehow large, right? Even if they're not very large, but you just have very many incoming signals, then what is getting into this neuron here is also a very large value. And why is that an issue? So what we have seen is how a neural network or a neuron works is we are collecting our input signal, right? We are multiplying it with a weight vector. I guess we transpose the other side usually, right? So we have our input signal, we have the weight vector, and then we apply a nonlinearity on top of it, for example, sigmoid, right? And how does the sigmoid look like? It's like this S-shaped curve, which somehow looks like this, right? So this is how a neuron works, right? Input times weights applied in the nonlinearity, which for example is a sigmoid, okay? If now the fan-in is very large, you can see that this term here might become also very large, right? What it means is then that it might happen that we are at the, let's say, in the domain of the sigmoid function, right? Which we have this S-shaped curve, we might be at the very end. We might obtain very large values, right? So here we have a very large in value for the sigmoid, which then means for the sigmoid here we are at this flat part, right? We are at the flat part of the sigmoid. So why is it bad to be at the flat part of the sigmoid? Because if we now compute the gradient, and this is what we are doing our gradient descent, right? The gradient here is 0, right? Similar here, in the very negative part, the gradient is 0, okay? So this problem is also known as a problem of vanishing gradients, which appears also here in this so-called weight scale issue, right? We have vanishing gradients because we might be at the tails of our sigmoid function, for example. And if we now want to do gradient-based learning, we don't get a nice gradient. The gradient is 0 and we can't escape, right? So this is very bad. So we want to stay somehow here in the middle because here we get a proper gradient. So the same, by the way, can happen the other way around, which is known as exploding gradient problem. In some cases, for some scenarios, we might have a very large gradient. And then, of course, training is also not good, as you know, because then it might, for example, lead to overshooting the actual solution, right? Because the gradient step is just far too long, okay? So weight scale is one important aspect, right? Because if it's getting too large, for example, because you have too many inputs or the same, if you do back propagation in the backwards path, if you have too many outputs, you might have vanishing or exploding gradients. So how can we then initialize our weights, right? We don't want to do it like all zeros or some constant value because then we get weight symmetry. Just doing random initialization is also tricky, right? Because then we might have this issue of having too large or too small weights. And indeed, there's one principle which is quite common to initialize these weights, which is called the Xavier initialization. And the core idea is simply that we want to preserve, or the question we are trying to answer is, how can we preserve the mean and the variance of an incoming IID signal, right? So ID, you know what this means, right? We just have independent draws, for example, from a Gaussian with mean and variance. And we want to preserve that the signal is preserved in the forward and backward paths. Simply speaking, right, if we feed in this IID signal, which of course is non-informative, we don't want, if we pass it through our neural network, that it either disappears or that it explodes, but we want that it still is like an IID signal with mean and variance. So with a 0 mean and 1 variance, for example, okay? So this is simply what we want to try to achieve, so to say. More simply speaking, we want to do this by controlling, so we want to avoid this weight scale issue by controlling the statistical moments of our weight distribution. And to make it a bit more clear, without digging into too much detail, you can look here at some examples. So what do we see here? So let's say we have a 4-layer neural network, and we train it over time. Right here you see the training. And let's say we don't do any specific tricks. Let's say we just naively initialize it in specific ways. Then what you could see, for example, is that while the first layer, so what is the first layer here? The red one is the first layer, and the second one is the green one, and the third one is the blue one. They still have some information, right? So the activation value, so this is the output of the specific neuron, they still carry some information. However, the fourth layer, right, it drops to 0, right? Because, for example, we have obtained too large input, for example, as we have seen it here, for example. Okay, and indeed, this is a common issue which you might encounter when you go for deep neural networks. It might happen that the first layers, they still have some information in them, while the last layers, the deep layers, all of a sudden don't carry any information anymore. Right? And this indeed was traditionally also a big issue why you couldn't train really deep neural networks, because the last layers, they don't carry any information because of some vanishing or exploding gradient information. So here you see it also in a bit more detail. What actually is happening is that while the first layers, layer 1 and 2, they still have some variation in their activation value. So remember, we're feeding in some IID signal, right? Here, this is not like a real image classification setting, but we're feeding in random data, so to say, with mean 0 and variance of 1. What you see is that while the first layers still carry information, the last layers, we're getting some peaky activation function. Okay? So simply speaking, we cannot really, the last layers, they don't contain any information anymore, because we didn't carefully initialize our model, and then after some time, we convert to a solution which is not too helpful. Okay, so what we indeed now want to achieve is the following. We want to initialize it in a specific way, these ways that after this training, the fourth layer or the fifth layer, they don't converge to this all 0, right? Which is done if we use this Clairaut initialization, which I'll show you on the next slide, which then hopefully at the end of the day leads to this behavior, right? And you see here now that the activation values, which we see here in these different layers, they all have still the same shape as the input signal, right? Again, the input signal, 0 mean, unit variance, and you see that also for the later layers, we have still here some variation in the signal. Okay, so this is essentially the goal of our initialization. If we don't do this, we end up here. If we do this clever initialization, we end up here. Okay, good. So how can we do this now, right? And here, I don't show you how we can derive this. I just give you the final result. So we can indeed preserve our signal's properties, meaning here this mean of 0, variance of 1, by using a weight matrix, by using weight matrices, which also have a specific mean and variance. Namely, that the weight matrices also have 0 mean, which is somehow natural, I would say, right? That the weight matrices also have 0 mean, then the signal's mean is also preserved. But the variance should have this kind of property. Okay, so for every layer, for every fully connected layer, we want to initialize the weight matrix in such a way that the variance of the weights, right, the variance of all these different numbers is equal to 2 divided by fan in plus fan out. Okay, so if we do this, then we ensure that in every layer, our activation also still has the same properties, so to say. Okay. So how can we do this more specifically? Because this, of course, multiple different initialization fulfill this property. One is this Xavier initialization, what I just said. So for example, you can initialize your weight matrices in a specific layer by sampling from a uniform distribution in this range. Okay, so you have this fixed range, which depends, of course, on the fan in and fan out of your neuron. And then you sample just uniformly across this range. And you do this for every element in your weight matrix. And this is your initialization, which has zero mean, which you, I guess, clearly see, right? Because it's a symmetric around zero distribution and has a specific variance. Okay. So this is one way of having a good initialization, which does not have this problem of having like disappearing activation values, so to say. Okay, so this is what you can usually do. One remark though here is if you, for example, use a regression task, right? And you know that in the regression setting, the last layer, there you don't use any activation, right? You can use the logit, so to say, as your prediction. So what you should be careful is that for the last layer, it's best to really take into account the target scale. What I mean with this is the following, right? So here, this Xavier initialization, so to say, initializes the weights that they are in the range of 0 plus minus 1 variance. Okay, if you know, for example, that your target you are predicting is around 5, right? Let's say that the targets you're predicting here, the targets you're predicting are around, I don't know, let's say it's around 5 plus minus a specific variance, right? Then of course you should make sure that your weights in the last layer also initialized in a proper way, right? Meaning, for example, you can on one hand put the bias term in this last layer that it accounts for the target scale, let's say a shift of 5, right? So not a 0 mean, but a mean of 5, so to say. And of course you can scale up also the variance in the weights to match the variance of your target, right? So what we mean with this target is, for example, if you want to predict the income of people, right? The income of people in, let's say, in euro amount, of course, does not have a mean of 0 and does not have a variance of 1, right? But has a larger mean and has a larger variance, right? And then you want to scale up the weights, so to say, and potentially also shift it to take into account the target scale for the last layer in a regression setting, for example. Okay, good. So this is the weight initialization. So why did we do this again, right? We did this that we want to avoid, on one hand, that the deeper layers, that they don't get any values anymore. And more technically, we also want to do this to avoid this vanishing or exploding gradient problem, right? Because we have seen if we're in the tails, for example, of the sigmoid, the gradient becomes 0 and then we can't learn. And indeed, this is a general problem, which is not just relating to the weight scale, but it's also relating in general to deep networks, or specifically also an issue which was always present in recurrent networks, so standard RNNs, and this problem of vanishing and exploding gradients. And I want to show you here in a one slide what this actually means in this somehow semi-formal way. So let's say you have a deep network, right? And let's say even you don't have any activation functions, right? You have a deep network which simply gets your input, right, and multiplies it t times with a specific weight matrix. Okay, so let's say you have layers, right, and every time you multiply with a weight matrix w. Okay, so a deep network. So what does it mean? So let's say we have this weight matrix, right, our parameters, so to say. Of course, we can do a decomposition, right? We can decompose any matrix in a specific way, right? That we have like the matrix V and V inverse, and we have here diagonal matrix. Okay, so let's assume this that we have this decomposition given. Okay, so what does it mean that we multiply our input signal, let's say x here, say we have here x, and we multiply it multiple times with w because we have multiple layers, right? Of course, it simply means that x is multiplied with w to the power of t to the power of number of layers, right? Which then, giving this factorization, of course, simply means we have here, again, v and v inverse, and here we have our diagonal matrix to the power of t, right? This happens if you write this down in this factorized form, okay? So this happens if you have multiple layers of multiplying with these weight matrices. So why is this now an issue? And here you see quickly why this is an issue. So in this matrix here, which is factorized in this way, we see that we have here this diagonal matrix in the middle to the power of t. right? We have a diagonal matrix to the power of t, which means if the original diagonal entries here, if they are smaller than 1, right, then this term here will quickly go to 0, right? If this is smaller than 1, this here will quickly go to 0. Meaning, if we want to compute now the gradient will become very, very small, right? On the other hand, if this here is larger than 0, right, this term exactly here will explode. It will become too large, right? And also then the gradient computation and all these calculations you're doing, they might become extremely unstable, right? Because you have very, very strong fluctuations, so to say, in your model, okay? So having here this deep layer, so to say, right, many, many times, here shows you quickly why you can have vanishing or exploding gradients, simply because of some analytical observations. Of course, this is a very informal explanation. Of course, in practice, you don't have always the same weight matrix and you have like activation functions in the middle. But in general, you can observe if you're not careful and you just stack multiple many layers, you can quickly come to a point where your gradients either explode or vanish simply by some analytical properties of your function, so to say. And what we have also seen right here is again written, we can have this saturation effect, right? That we are in the tails of our activation functions, for example, then you also quickly get like vanishing gradients. So what are the solutions? I mean, there are multiple solutions. You can, for example, use other kind of components, other neural network layers, right? So for example, for sequences, there's a classic RNN architecture, and then more modern architectures are like LSTMs and so on and so forth, right? So different architectures help you to avoid this issue. But there are also other tricks like batch norm, we talk about this later, or we can also change just the activation function, right? So for example, the sigmoid is let's say rather tricky, right? Because we have the saturation in the in the tails. But for example, if we have the ReLU activation function, at least here on the positive side, we always have a proper gradient, right? We only have this saturation aspect in the negative part. Okay, so changing the activation function might also help. Or of course, if you have like this exploding gradient problem, you can just do gradient clipping. That's a very simple ad hoc solution, right? You say, okay, I want that the gradient is not larger than some constant c, right? And if it's larger, you just clip it to make sure that the gradient update step is not too big. Okay. But in general, even though in principle a deep neural network looks very simple to train, right? Because it's just a function and we can do backpropagation and so on and so forth. In practice, it was and sometimes it is still hard to train because we are always relying on gradient-based training. And if the gradients are not informative, if they are 0 or too large, then we cannot learn, right? So theoretically, all these deep neural networks are easy to handle, so to say, right? But from a practical side, really training them is actually not always very easy. Okay, so then one other point talking about this training is of course also regularization, right? Because we have seen that neural networks in general are very powerful because also they have these complicated transformations which all require to train some parameters. Remember again, in a fully connected network, we have all these parameters between these two layers, so to say. Even at CNN, in a convolution network, we have these windows which reduce the number of parameters, but still there might be many. Right, because you have very large filters, for example, you have all these different channels, for example, there are still many parameters. So indeed, neural networks in general are models with a very high capacity. And you know what this means, right? This means that there is a potential problem of overfitting, okay? But you already know how to prevent overfitting, right? One way is to do regularization, right? And indeed, you often do this also in neural networks. You just add a regularizer, making, for example, sure that the L2 norm or the Frobenius norm of the weights, for example, is also added to the actual loss, right? You have your standard loss like cross entropy and you have your regularization. And now you want to minimize this term, for example, so usually with some regularization parameter, of course. Okay. So this, of course, also works in neural networks and prevents overfitting. Okay. So we can also have different regularizations, not like here Frobenius norm, L2 norm, but we can have L1 norm, which leads to more sparse solutions. So more of these parameters are 0, but this is also what we don't want to dig into too much detail here. And then there are many other techniques to avoid overfitting. And to achieve better generalization, you can, for example, think about data set augmentation or data augmentation in general, right? So for example, if you look at images, of course, you know that if you have like an image of a cat, it's still a cat if you do this translation, or if you do like a rotation, or if you slightly change the lighting, right? But if the neural network is not seeing this, but if it's not a specific neural network which knows that rotated images are the same, right? Then you, for example, can do dataset augmentation, right? You enrich your dataset, adding all these rotated versions, and you train with these augmented dataset. This leads to better generalization because the network has seen these kind of different variations, okay? In general, you can also just inject noise, right? You can add a bit of salt and pepper noise or some Gaussian noise on top of it, right? And then you also get a larger dataset and augmented data, and the model might generalize better because it has seen a larger variety of data sets. One other point I already mentioned, right, is this parameter sharing, parameter tying, right, that you reduce the number of parameters, for example, with these convolutions. And then, of course, you also prevent overfitting because we have reduced the number of parameters. And last but not least, there's also a principle of dropout, which can also help you to do better generalization, which we now will explain in more detail because it's a very prominent principle, which is very famous in neural networks. So what is dropout? In dropout, essentially you take your neural network, okay? So here we have a two hidden layer neural network. And what you do is you randomly deactivate, drop out specific neurons, for example, right? You see it here. So for example, here we have like 2 layers with 4 neurons each, but in every iteration of your training, right, in every gradient step, you drop out a specific fraction of neurons. So for example, usually with 50%, let's say, right, you see here, these are dropped out and you only keep these here, okay? So what does dropping out mean? Dropping out technically means that more or less, for example, you put all these weights to make them 0, right? Because if you remove this neuron, essentially there's no flow of information here, which means that these weights here become 0, so there's nothing flowing in, right? So technically you make the weights 0, which are here, okay? So this is how you realize it. So again, in every gradient update step, you don't compute the gradient with respect to your actual full architecture, your full neural network, but simply speaking, you compute it with respect to a subset of your architecture, okay? So why does it help to prevent overfitting, to promote a generalization? Because what you're now actually doing is you do not train your weights based on one architecture, right? Based on one fixed architecture, but you are training your neural networks based on 2 to the power of h different architectures, h being the number of neurons you have here, right? Because every neuron can be activated or not, right? And every time you get a different architecture. So here you have this architecture with these 4 neurons. Next time you might have these 3 and this neuron, for example, right? Every time you get a different architecture, so to say, and you train the corresponding weights, or you update the corresponding weights. So the weights you are getting at the end, right, once your training has converged, hopefully, are weights which work good for all these different kind of architectures, right? These are not weights which only work for the full architecture, but these are the weights which work good for all these different combinations, so to say, with all these different kind of dropouts you have sampled, okay? So this is why dropout also helps you to generalize better, because the weights are a compromise between all these different kind of architectures, okay? So you can specify, of course, different dropout probabilities, right? You can make it smaller or larger. And of course, as usual, you should monitor careful how your training behaves, right? Whether you are still able, for example, to really fit your data to get a good loss, okay? But in general, this is a good principle to also avoid overfitting. And then finally, some more tricks here, right? You see, this is all different aspects you should have heard about and you might want to use when training neural networks. It's all a lot of engineering as well, right? And talking about engineering, of course, also hyperparameter optimization is one big deal in neural network design, so to say, because we have already seen that neural network means we have to specify specific aspects. We have to specify the number of layers, number of units per layer, which activations we want to use, which optimizer. Learning rate, of course, is always an issue because we do gradient-based training. We talked about this data augmentation and so on and so forth, right? These are all hyperparameters you have to pick. Of course, what you can do is you can just play around with it, right? You have a proper train validation test split, as you are aware of, right? And you should monitor on the validation set what works out, right? How does your training behave, right? Do you achieve a good loss? So does it go to 0, for example, and so on and so forth, okay? So you can do this playing around. And of course, you can do it also in a more, let's say, sophisticated way. You can do so-called hyperparameter optimization. I mean, you can really do some optimization on the hyperparameters. So for example, by doing random search, which is still more like playing around, or by using Bayesian optimization, okay? So there's a big field of, for example, AutoML, automatic ML, where they do this hyperparameter optimization or neural architecture search, where they try to automatically find the right architecture, right? And sometimes you can think about this as like a big meta framework around it, right, where you test all these different architectures and you try to automatically find a good architecture by doing different kind of optimization principles, okay? So the big challenge here is, of course, that many of these choices are like discrete, right? So the hidden layers, for example, this is not something where you can do gradient descent on top, right? Because these are discrete choices. So this optimization are often kind of black box optimization principles. It's called like Bayesian optimization. So it's not straightforward to do this in a like say in a principled way, for example. But in general, main message here, hyperparameters are extremely important for neural networks. I would say even more important than for the classic models you have learned so far. And yeah, you have to find these, unfortunately, in some kind of an engineering exercise, you have to find out what are the right choices here for your specific data and for your specific task at hand. So one last remark here. In some cases, you can do this more automatically. I said already, this AutoML or this kind of neural architecture search. And indeed, for example, if your hyperparameters are continuous, you can, of course, also try to really learn these hyperparameters again, right? So meaning you can use, for example, gradient descent on the hyperparameters. So for example, you can do gradient descent on the learning rate. So what we mean with this is that now technically you have to do a so-called backpropagation through the training procedure itself, right? Because changing the learning rate means, let's say you initialize, and you see it here, right? Let's say you initialize your weights, right? And you pick a specific learning rate. Then your learning will behave in a specific way and you converge here, right? You have found specific weights. If you pick a different learning rate, for example, your learning procedure might work completely differently, right? So these trajectories correspond to like your trajectory of gradient descent update steps, right? You're following a specific loss function, you end up here. And a different learning rate, again, means a different trajectory, right? So what you can think about, and this is called like meta learning, you can, or learning to learn, right? You can try to learn these hyperparameters. So what is a good learning rate, for example, such that I end up at a specific good point, for example, okay? And what this requires, again, requires that you have to do backpropagation through your training, right? Because now your function you're evaluating is no longer just a determinist, it's not a neural network, right, where you have an input and an output, but actually where you want to optimize over is starting from here with a specific learning rate and you end up here, right? So essentially your function is starting here, output is here, and the learning rate is a parameter of your function. Starting here, different learning rate, you end up here. So you have to propagate through this learning procedure, right? And then if you can do this, right, you can do a so-called meta update, meaning you can try to set the learning rate in a better way such that it leads to a better training. So why does it make sense, right? So you can use it, for example, to do a few short learning, right? So for example, what you can do is you can learn the initial weights of a model, not just the learning rates, but you can learn initial weights of a model, for example, such that if you have only a few training examples, right, you only need a few steps, for example, then to find to have these good weights if you have only a few training examples, right? I mean, what I meant is, let's say you first learn in a meta session what are good initial weights of your model, right? And now think about, you have a new data set, right? Some new images like a few cats. You know that you take these weights you have learned before, these initial weights you have trained before in the meta setting, right? Not the final weights, but the initial weights. And starting from these initial weights, you do here a bit of training, right? And since you only have a few training examples, you might only want to do a few training steps to not overfit. But hoping that these initial weights we have learned before also help for this domain, you might do a good job also for these few training examples. So this is then often called like few short learning, because you only have a few examples. You cannot really do a full-blown training, but you have to do something. And yeah, these initial weights you learned before might be a good idea. Okay, so one point, of course, for large neural networks, this is extremely expensive, right? So backpropagating through this training procedure, right, is of course extremely expensive, right? So this was just here a quick side discussion that in principle you can learn all these parameters again, right? You can learn all these hyperparameters technically at least, but it's becoming more and more expensive because it's no longer just some input and some deterministic output based on a neural network, but it's some input and then a very complicated function, optimization function, which gives you the output. Okay, so with this then we are almost at the end here. So what we have seen is really like now the one specific architecture, CNNs, which helps you to exploit the knowledge, and we have seen specific tips and tricks already, right, which are important to make these networks trainable. So in the next part, we want to continue with a quick introduction of these deep learning frameworks and some more tips and tricks. But before that, let's take a quick break.